discussion is Stokes' law, okay, and we shall derive the equation of the terminal velocity, and that is our main point here. Now see, Stokes is a name of scientist, and he said that viscous force, that is Fv, viscous force is Fv on small spherical solid body of radius r and moving with velocity v through the viscous medium of large dimension have coefficient of viscosity eta, then that viscous force is 6 pi eta r v. So this is the equation of Stokes' law. Now see, we consider it, or rather we try to understand this. Say for example, this is the small spherical solid body and it is moving in the viscous medium. Okay, one force, that is mg force, is in downward direction, buoyant force will be in upward direction, and the viscous force, that is a resistive force, that is also in the upward direction. Now see, we consider that the body is having radius r, density rho, it is falling in the viscous medium of density sigma. So here this fluid is having the density sigma. The density of this solid sphere is rho. Okay, now the equilibrium position, if you consider, so that the force due to viscosity, that is viscous force, that is shown here by F. Okay, this F is equal to F1 plus F2. Okay, rather this is a vector sum. Okay, or we can say, you can understand this way also, that viscous force F is the result of one force, that is its weight, that is F1, that is in downward direction, and F2 is the buoyant force, that is in upward direction. So resultant force will be F1 minus F2, that is equal to F. Okay, now this viscous force is fixed, that is 6 pi eta rv. Okay, now the weight of object, that is F1, that is in downward direction, and now see, this is the spherical body. So if you want to calculate this F1 force, then it is equal to m into g. Now mass is nothing but volume into density, and you have to consider the density of the sphere because mg force is acting on it. So volume of the sphere, okay, volume of the sphere will be 4 by 3 pi r cube, and multiply by rho will give you the mass of the sphere, and therefore the force F1 will be m into g. So that will be equal to 4 by 3 pi r cube rho into g. Similarly, the buoyant force is acted upon it, and this buoyant force is the force which is applied by the liquid in the upper direction, and for that we have to take the volume of the liquid multiply by density of liquid. So that F2 force will be mass of fluid, if you want to find, then volume of the fluid, that is 4 by 3 pi r cube, that is volume of fluid, into density of fluid, that is sigma, and if you multiply it by g, then that will be the force which is applied by the fluid on the object in the upward direction. So now you can understand it very easily that the resultant force, that is 6 pi eta rv, okay, 6 pi eta rv is nothing but 4 by 3 Okay, we can write this way. The resultant force, that is 6 pi eta r v, and this force, okay, that is in upper direction. Okay, if this force and the F1 minus F2 both are same, okay, if they are same, as such the resultant force can be written as, try to understand, the resultant force is nothing but 6 pi eta r v. When the forces are in equilibrium, then the velocity is a terminal velocity, it is denoted by 6 pi eta r vt is equal to 4 by 3 pi r cube g into rho minus sigma. And if you make Vt as a subject of formula, okay, then the equation of terminal velocity you will get, and that terminal velocity, this force I was talking about, and the forces are in equilibrium, then 6 pi eta r Vt is equal to 4 by 3 pi r cube rho minus sigma into g. And if you make Vt as subject of formula, then you get Vt is equal to 2 by 9 r square g rho minus sigma upon eta. This is the equation of terminal velocity. Okay, this equation gives the terminal velocity, and this terminal velocity is constant, and after that the object is moving with the terminal velocity, that is constant velocity, we can say. Okay, now upward motion of the bubble produced in the fluid, the density rho of air bubble produced in the fluid is less than the density of fluid sigma. Hence, rho is less than sigma, so terminal velocity is negative, and hence bubble would travel in the upward direction. Okay. Now we talk about the Reynolds number. Reynolds is the name of scientist, as such he was a mathematician, and he derived a number which is called the Reynolds number. The derivation is not there in our syllabus. Okay, just we have to remember this formula. Reynolds number is given by rho v d upon eta, where rho is the density of fluid, v is the speed of the fluid, d is the diameter of the capillary or a tube through which the fluid is flowing, and eta is the viscosity. Okay, now from the value of Reynolds number we can determine the type of the flow. Now if the answer of this Reynolds number is less than 1000, flow is streamline. If Reynolds number is more than 2000, the flow is turbulent. If the value of R is between 1000 and 2000, then the flow is unsteady. Okay. Now what is turbulent flow? Okay, when the flow of fluid is very large, the flow obtained is known as the turbulent flow. There are certain illustrations, say sea current, smoke rising due to the burning of wood, then stars twinkling because of turbulence in the earth's atmosphere, and the flow in the boat waves and around aircraft wing tips. Okay, these are the examples of the turbulent flow. Okay, now we have a formula of Reynolds number in the form of inertial force and the viscous force. Now see, Reynolds number is nothing but Re, that is rho v d upon eta. Now you can rearrange this, rho into v, okay, divided by eta, okay, and d can be taken in the denominator. Now if I multiply by v and divide by v, then I can get rho v square eta v upon d. Now multiplying and divide by a to right side of the equation. So now you are multiplying by a and dividing also by a. So this becomes rho a v square upon eta a v upon d. Now this rho a v square is nothing but inertial force, and this eta a v upon d is the viscous force. So we can say that Reynolds number is nothing but inertial force upon viscous force. Thus, Re can be represented in this formula also. Now the new topic is there, that is surface tension in the context of potential energy. Now see, the liquid stays together because of the attraction between the molecules. Molecules of the liquid are having comparatively more attractive force than the gases. Now consider a molecule A well inside the liquid. Now if you consider the liquid or a molecule which is there inside the liquid, that is this figure A, okay, then that molecule under consideration will have the attractive force from all other molecules around it, and the resultant force on this molecule will be equal to 0. Try to understand. Okay. This attraction result in a negative potential energy for the molecule, which depends on the number and distribution of molecule around the chosen one. But the average potential energy of all the molecules is the same for water. The heat of evaporation is of the order of 40 kilojoule per molecule, or per mole rather. Now let us consider a molecule near the surface, that is figure C and D. Okay, somewhere the molecule is here, okay, at this particular point, or somewhere here below the surface, slightly below the surface. Then this molecule is having the resultant force that is in downward direction, so it has a tendency of going down inside the surface. Okay. Thus, molecules on the liquid surface have some extra energy in comparison to molecule in the interior, because these molecules which are there inside are having resultant force as 0, so their energy is comparatively rather the molecule on the liquid surface have some extra energy. These molecules are having less energy. Okay, they cannot escape, but these molecules, you can understand that they may escape if they get the energy from outside and they become evaporated. Okay, a liquid thus tend to have the least surface area. So what will happen? These all molecules will try to move inside. So whatever energy they are possessing, because of that this liquid surface is having a tendency to contract slightly. Okay, this property is known as surface tension. Since the liquid consists of molecules moving about, there cannot be a perfectly sharp surface. The density of liquid molecules drops rapidly to 0 around z is equal to 0, that is on the top of the surface. Okay, where z is 0, okay, what will happen? The energy is almost becoming 0 here. Say for example on the surface they have very less energy and they may go out. Okay, a larger of thickness r0 below the free surface of liquid is called the surface of the liquid, or we can say thickness of say value r0. Okay, that is called the surface of the liquid. Okay, thank you very much.